Okay, colleagues, I think it's time to start. So first of all, I send to the Zoom chat the link to the slides. So that's it. So if you want, you may download it. Also, I would like to announce our next seminar. So next week, we will have a seminar at the same time. The speaker will be Juan Torres from Institute of Photonic Sciences and the University Politécnica de Catalunya in Barcelona. And he will talk about optical coherence tomography with an SU11 interferometer in the high parametric gain regime. Okay, and now our speaker is Juan Loredo from Center of Nanoscience and Nanotechnology in Paris, and he will told us about solid state based sources of non-classical light. Juan, please.
Okay, thank you. So of course I would like to begin by thanking you, Konstantin and Ivan, for this very kind invitation. Apart from having met Ivan in Paris, it is really the first time I'm in contact with the quantum community in Russia. So it's very nice to hear and learn about your research through this series of online seminars that you're organizing. Also, it's interesting to me to see that some of the quantum optics community from Brazil is part of the audience. And as I was briefly mentioning before, this is particularly interesting to me because I did spend some time in Brazil, at the Universidade Federal de Minas Gerais, working with Carlos Monkenden some years ago, and I only have very nice memories of my time there. Okay, before I continue, what I must say first is I should apologize in advance if something happens because unfortunately lately I've been having some trouble with my computer, and sometimes it just decides to shut itself off for no reason. So if that did happen, I apologize, and I'll make my best to try come back up online as soon as I can. Okay,
Yes, sure.
Having said that, again, my name is Juan Loredo. I am originally from Peru, but I went on to doing my PhD in Australia at the University of Queensland with Andrew White in Brisbane. And then later on, I moved on to doing my postdoctoral work in Paris in the group of Pascal Senelat. Okay, so continuing on the nice talks that I've seen from this series of seminars on non-classical light generation, today I will be discussing similar approaches, but this time based on the solid state technology. Now, there will be some overlap between my talk and the talk that Nicholas Omaski gave a few weeks ago, because our work is very closely related since we actually share the same projects. We've been sharing the same project for a few years now, but I will make an attempt to not repeat many things that you already heard from his talk and instead focus on some other things that were not covered. Okay, so the work that I'll be describing today was carried out at the Center for Nanoscience and Nanotechnology. This is in France. And the institution, let's move on. The institution, here is a picture of the institute I took one sunny day. Now, it is made of some 400 or so researchers, from permanent researchers to postdocs, students, engineers. But the results I'll be presenting today were taken in this group of 20 or so people led by Pascal Senelat. And now, if I could summarize in one single slide what we do, I'll say, oh, let me just turn this up. Yeah. I will say we work on quantum optics with artificial atoms. We develop solid state single photon sources that look like this miniaturized, this pillar, this cross image here on the left side of your screen. That these are really miniaturized pillar structures that some tens of those can fit in a chip that is the size of a thumb now. And now these chips have evolved to a point where we even have built-in electrical contacts that allows us to tune the properties of our devices. They are semiconductor, single semiconductor quantum dots embedded in some cavities that I will explain shortly. Okay, but why do we do this? We work with these devices because we are interested in finding applications in technologies of the second quantum revolution, right? And these technologies have four main pillars. One, as you are very well aware, one is the secure distribution of keys for allowing remote parties to communicate securely with a security guaranteed by the laws of quantum physics themselves, to building devices, measurement apparatuses that can obtain the values of physical properties with a sensitivity, a precision that it goes beyond what can be obtained otherwise by these so-called classical measurement devices instead. To also other interesting protocols like the simulation of some physical processes that are quantum in nature, that are typically very difficult to simulate or run in a classical computer, for example, and that have very interesting applications, for example, in the discovery of new materials and in drug design, and as well the holy grail of these quantum technologies, which is to one day build a fully functional quantum computer. No? Now, the images I'm putting here, they do not necessarily belong to degrees of freedom of light. In particular, the chip I'm putting here, this is a chip that works with superconducting circuit technology, and it's a chip made by Google, and last year used to demonstrate quantum supremacy. I'm sure you all know that already. But all these technologies are indeed possible to be realized with light, in principle at least. And in order to do so, what we need is non-classical resources, right? In optical degrees of freedom. And these resources come in this form, like individual particles of light, like single photons, or also particles of light or photons with their properties correlated, or entangled photons, for example. Even bright light sources with noise very much reduced as compared to classical sources, and for example, in discrete states. But what I will argue, and I will describe a little bit in this talk, is that now we are enabling a new resource, a new non-classical resource. And this will be a photon number superposition. So now the photonic state will have coherences in the photon number, will be a superposition of photon Fock states. Okay, now let's move on. So this brings me to the brief outline of the talk. And it is as follows. First, I will describe very briefly, so we are all in the same page, how quantum dots work as artificial atoms. Then I will tell you about how to create light in a photon number superposition. And I will finalize with some applications where we utilize these sources that we make. Okay, so let's begin by the beginning. So what is a quantum dot? Basically, a quantum dot is a nanocrystal. It's a piece of semiconductor of some tens of nanometers that is embedded inside another bigger host semiconductor with a bigger band gap. And this works in such a way that due to quantum confinement and to the dimensions of this apparatus, although the quantum dot itself is made of tens of thousands of atoms, they all behave as a single atom, and therefore they are an artificial atom, because a single electron hole pair can be hosted, excited, contained in this quantum dot. And because of this confinement, then upon recombination of this electron hole pair, this exciton state, a single photon is emitted. So now these devices can in principle be deterministic sources of single photons, but usually the first problem that is encountered there is the collection. They're normally, although they can emit the photon near deterministically, it is usually very difficult to collect them, to extract them from their host material. So the approach that our group, and by now many groups have followed, is to exploit a cavity QED. And one can imagine if you embed this artificial atom, this quantum dot, in a cavity mode, then you are forcing the atom to emit in the mode of the cavity, right? It's a more friendly mode. It could be a single mode cavity with nice Gaussian profiles, useful for many other things. So a little bit of the schematics of how the device looks is like this one here. We have a quantum dot in the middle of a bunch of pairs, or these DBR, distributed Bragg reflector mirrors. And what they are is they are just materials of alternating layers of alternating refractive indices, such that via destructive interference, they behave as very reflective mirrors. Now, just a few words on how do we make them. It all begins in the clean room with this molecular beam epitaxy machine. And as many of you already know, what these machines are, they're basically big chambers kept at ultra high vacuum levels. And they have some of these pure elements inside, pure semiconductor material inside. And by controlling some shutters and the time the shutter is open, and what we can control and evaporate some of these materials and redirect them to a central location where the grow starts to begin. And there, what is very nice from these machines is that you can grow a material of given semiconductor material, one atomic layer at a time. And this allows you to construct very precise structures. So for example, one could imagine then simply growing a planar structure of gallium arsenide and aluminum gallium arsenide. This is what will constitute the, let's imagine an eventual bottom mirror of our cavity. And at some point, then some indium is instead spread over this layer, and you begin to grow the quantum dots. Now, here it's important to know that the quantum dots are initially grown in a random position, right? So this is still fine, it's part of the process. What you do next is you build the second part of the mirror, well, the top mirror, and then you're left with a big planar structure with a bunch of quantum dots randomly positioned somewhere in there. What you do next is you place a polymer photoresist on top, and after that you start to investigate your sample. You start looking for the quantum dots. So you go to your confocal setup, you shine the sample, you collect the emission, and you do these maps over here that tell you where you have the quantum dots. And after you identify lines of interest, what you do next is, well, then you expose that photoresist to leave marks and to distinguish the regions of interest in your sample. Because after, what happens is you do the etching process, and then only those parts that were exposed are left in your sample, and therefore you are left with these micropillars now with a quantum dot in its center. Okay, so now this technique has evolved in the past years to the development of these kinds of sources that have a more complicated structure. Instead of being isolated micropillars, they have this cross structure with bigger structures attached to it. And the idea of having these kinds of structures is to be able to have a bigger place where you can come with a wire bonding and eventually define your electrical contact by that. Okay, now, so when that is all done, what happens next is that we install the samples, we put the samples in a cryostation where it is kept at some Kelvin from 4 to 8 usually. And what we do after is we place this very simple optical setup on top of the cryostation chamber. It is just a dark field microscope in order to that allows us to do resonance fluorescence experiments. And although it's very simple, it is very powerful at the same time, because if you can see here, how this works is that you are sending a laser pulse to that polarizing beam splitter, and then that laser eventually goes to the quantum dot, but then it comes back from the same path where it came from. And then there is a different output here mode that contains only non-classical light emitted by the quantum dot. Now, so this means that now we have a fiber with non-classical light inside. So we can start by characterizing the properties of this single photon, right? How much of a single photon it is. So we can measure its second order correlation function is G2 in a standard Hamburg-Brown twist experiment. And then we know that for a perfect single photon, the result of this measurement should be 0. And then the numbers that we usually find are in the few percentages here. Now, there are reasons that change what kind of value can you get or what can limit this value of G2. These reasons are not too important right now. It has to do with the nature of your emitter, with the transition, whether it's a neutral or charge exciton. It's not important right now, but usually we can get values around this number of a few percentages. So it is a reasonably good single photon source. It can be further improved with some details that, again, will not be important to discuss right now. And what about the other figure of merit then, which is the indistinguishability of the photons? As you all know, what happens when you send two photons into a beam splitter, they either output the same, they either follow the same output or they cross. And if the photons are quantum mechanically indistinguishable, these elements, the last elements, should vanish. Their amplitude, probability amplitudes cancel out. So by measuring how often these events occur or how often they're being suppressed, we can put a number on the degree of indistinguishability of the photon. Okay, so regarding this number, the values that we normally get from the sources are in the 90% region. Again, this value can be increased furthermore with some of these details, like, for example, erasing the photon sideband. But usually in the conditions where we use the source, we run it with values around this number over here, 90%. If you would like to have some more information on our devices, I invite you to see these references and also more recent references from our group. Now, so far what we have is a single photon in a fiber, right? And it is a non-classical state. And what these states are good for and how they can be used in optical quantum technologies is via the exploitation of superposition and entanglement. If you can use a single photon and put it in a superposition of polarizations or paths, for example, or even time or colors, then you can start using that in optical quantum technologies, right? But what about the degree of freedom I was mentioning before? Are there superpositions of photon number? Have people done experiments of this kind? And the answer is yes, people have shown states of this kind actually several times in the past, but the problem is that you have to always engineer the state. So this state is a result of a complex experiment that uses interference, it uses conditional measurements, and at the end you produce a state, but you produce it really at very low rates. And a problem for this is that at least so far there was not any emitter of this kind of state known in nature. Well, until now, because now I'll show you that actually quantum dots are natural emitters of these states. That's the state that a quantum dot emits is a superposition of photon numbers, has a lot of interesting features in exploiting this degree of freedom. So this brings me to then explaining you how do we get these photon number superpositions in the first place. Well, we can realize this by just recalling something very simple, right? What happens if you have an atomic system and you drive it resonantly? You know, you can have the state of the atom in a genuine quantum superposition of ground and excited state. Then you can try to think of what would happen then when a spontaneous emission occurs, right? You can ask yourself, of course, because if the atom was in the excited state, after a spontaneous emission occurred, then it would have emitted a photon. And if it was in the ground state, it would have emitted not photon. So you can ask the question, if the atom was in a superposition, also the emitted light should be in this superposition of photon numbers? And we can start probing that question because we do have this artificial atom. We drive it resonantly, as I was explaining before. And we can see signatures of this resonant driving in Rabi oscillations measured here, right? Now, one thing I should say is that we have an update. Before we used to measure between 1, 2, 2.5 megahertz directly detected. And now our devices have improved in different ways. They have improved their efficiencies themselves. They have We are using better detectors. We're using superconducting nanowire detectors. And one of our latest numbers and best numbers so far is that we are measuring near 8 megahertz, 7.7 megahertz of light, of single photons. So this means that because we are starting from an 80 megahertz source, so right now, 10% of the time we actually detect a photon, right? This will be very, very important when we want to do multi-photon experiments. Okay, so let's go back to the question. Can we have a photonic state in a superposition of photon numbers? Can this coherence be mapped from the atom to light? And the answer will be yes, of course. And how can we probe this? How can we make an experiment to know that? Here we can just recall for a second what happens to us, maybe those who have done the experiment in the lab of doing of getting two photons from down conversion, collecting them in different fibers, and then sending them to a beam splitter, right? When we have done this, what we do is we place two fibers in front of a beam splitter, right? And as you can imagine, these fibers really at the microscopic, submicroscopic scale, they have different lengths, and in fact, their length is varying because of the environment. You can have some temperature fluctuations in your lab. And the point is that really when you do the experiment, this Honomandel experiment with two single photons, you also have a phase term that normally you do not consider at the input, but you do not consider as well because you don't see anything that depends on this phase. All that it happens when you send two single photons, let's say from down conversion to a beam splitter, is you get this, you produce this Nun state, and the Honomandel effect tells you the output state will be this one over here. And nothing depends on the phase. But we could also make a simple calculation of what would happen if instead the input state is a superposition of the single photon and a vacuum. And it turns out that now that phase is important. There are quantities that depend on this phase. For example, just the mean photon number at any output of the beam splitter. It turns out that it oscillates as a function of this relative phase in the input, and it oscillates with the visibility term here that is equal to the vacuum component, in fact. That's also why when the vacuum component is 0, then you see nothing, you see no oscillations. So here we are saying that a superposition of vacuum and a single photon in this very simple experiment leads to oscillations in the mean photon number with a visibility equal to the vacuum, right? Now, we can also extend a little bit the state that we are assuming as an input, and we can say, okay, what happens if the photonic state is not fully indistinguishable? What happens if you have some degree of indistinguishability at the input? And if you do the calculation, you see that all that it does is just tunes and rescales the visibility of oscillations that you should observe. As well, you can then ask yourself what would happen if the state is not pure, then if it doesn't have coherences in the photon number, but instead is mixed. When you do that and you introduce this mixed parameter here that is 0 for fully mixed states, well, you also find that the visibility of oscillation should be rescaled. Okay, so what this means is that if you do an experiment where you send two that you believe is a single photon, or you don't know if it's a superposition with vacuum, and you interfere them in a beam splitter, if at the output you observe oscillations in the mean photon number, what is measured with a single detector, this implies that you must have coherences in the photon number. Now, here are two specific examples of what I just said. Very simple calculations of what happens for a pure state. You observe that there are these oscillations with respect to the phase that I was describing before. And for the case of the totally mixed state, there is no oscillation whatsoever, right? So now we can wonder what happens in our case then. And all that we do is we just do this experiment at different parts of the Rabi oscillation from 0 to pi pulse excitation, or even beyond that I will describe shortly. So what happens? Yes, the experimental setup that is used to do this experiment is very, very simple. This is the standard Honomandel experiment for the quantum dot sources. What you do is you probabilistically send consecutive limited states into the different inputs of the beam splitter by using a previous beam splitter and a delay line. But it's basically, this can be just simplified to having two of these states interfering of the beam splitter. Okay, so now, if we go and place our state below pi pulse excitation and somewhere between the ground and the side state for the atom, well, we find that when we perform the experiment, there are indeed these oscillations between the counts detected by either detector at the output of that beam splitter. Now let's remember that we said that this visibility should depend on the amount of vacuum you have in your state. So we can just place ourselves somewhere else in the Rabi oscillation curve. And for example, with less vacuum on the point where vacuum is minimized in the pi pulse excitation, and indeed we see that the visibilities are decreasing. And we can also do the contrary, go somewhere else in the Rabi oscillation to maximize vacuum. And then we see that the oscillations are increased in time. Now, these measurements here, they are not following a fixed value of phase or a varying value of phase, really. And they are plotted versus time. And the reason is because we actually discovered this without really, we realized this was true without looking for something like this. We were performing our standard experiments and suddenly saw that there was something strange there in the statistics, that the detectors were oscillating, the counts of the detectors were oscillating, and initially we didn't know why. So that's why the measurement here, this is the first measurements that we took, they actually are plotted versus time as opposed to the phase. Okay, now, so we can start tuning the parameters that we have available, like for example, the amount of vacuum by simply choosing where in the Rabi oscillation we are located, or we can also tune the degree of indistinguishability of the single photon component, like for example, playing with the relative polarization. And by doing that, by tuning the parameters we have available, we can actually put numbers on this lambda parameter, which defines the purity in the photon number basis. And when we do that, we found near unity values of photon number purity. So this was very nice. This means that we have a very high quality source of photon number superposition states. No? Now, enough of this. We can also imagine that at the input, we not only have a vacuum and a single photon, but we can just extend that to an arbitrary number of photons. You have a superposition of 0, 1, and up to m, any number of photons, and you can do the same calculation. And basically, these are just a little bit of generalized results for what I showed you already. What a single detector would measure is also a quantity that varies with the phase of the experiment, but now the visibility is given by a little bit more complicated form that depends on the photon number distribution of your input state. This is not very important right now, but it will be useful for another case in which we find that we're able to also have two photon emission and have states that are a superposition of vacuum, a single photon, and two photons. Okay, I'll just move on this slide. So now I will describe that part. How can we get two photons out of the quantum dot? Well, you can simply drive the quantum dot on 2 pi excitation. This is the first minima after pi pulse, of course. In order to understand why we can have two photons emitted on 2 pi excitation, we can think of the following, right? In order to reach to 2 pi pulse, we have to pass first through the pi pulse point. But at this point, you have the largest probability of emitting a photon already. So you have a non-trivial probability of emitting a photon. And then your system has absorbed a pi pulse of energy, but you sent 2 pi, right? So you are still left with another pi pulse of energy that can re-excite your system. And it's this re-excitation process that gives you the two photons in the first place. And what is interesting from pumping your devices on 2 pi is that actually the two photon component is favored and is larger than the single photon term in the photonic state that is emitted. Okay. And a signature of this behavior is that when you do a second order autocorrelation measurement, you find G2s that now, unlike the values of 0 that we were observing before. Now we have values that can, in principle, depending on the amount of vacuum that you have, be as large as it's boundless. It can increase to very high numbers depending on how much vacuum you have. Okay, so now we perform an experiment similar to the one I described before. Very simple experiment. We just interfere the photonic states that are that result from driving your quantum dot on 2 pi pulse excitation, and then we do see what we were expecting as well for the case in which we had 2 photon emission. Now, by doing these experiments and by measuring a bunch of visibilities of all kinds of single photon, single detector visibilities, coincidences visibilities, we can start putting numbers on our photon number distribution as well. And then what we find is that the photon number distribution is actually quite interesting. It has a 2 photon emission larger than a single photon component. And the reason why this is interesting is because it is numerically close to other states of interest in the literature, like, for example, a small Schrodinger cat state. So it turns out that the states that a quantum dot is generated on 2 pi is numerically close to a cat state of size of around 0.5. Or details on this we can discuss a bit later. But if you would like to know more of this, please either ask me in the question section, or I invite you to see the reference where we published this last year. Okay, now this brings me to what kind of applications then we can envision, and where have we already utilized the sources that we make. So the idea is, of course, to grab these sources of non-classical light and start merging them and using them in some quantum computation or simulation protocol. So among the things that we have done is build devices that look like this, and I'll explain you very briefly what this device is. This is just a bunch of electro-optical modulators and polarization sensitive elements like PBSs, and all that they do is, when they work together in some synchronized way, what they do is they receive an input of single photons or photonic states that we described, and they selectively send different time beams to different spatial modes this time. So what this device does, it transforms a train of single photons that are all in the same mode, but in different temporal modes, to a bunch of single photons, for example, that now are in different spatial modes and all at the same time, in the same temporal mode. So a specific case of this device we built indeed for an experiment that we did in collaboration with the groups of Fabio Schiarrino and Roberto Selame in Italy. And here, this is a little bit what was already discussed in the talk of Nico, but we performed this multiphoton interference experiment on chip, no? So what is interesting to know here, that in this experiment that we realized over a year, or maybe the data was taken near 2 years ago, we could generate these 3 photon states at rates of 4 kilohertz or so. And then for those of us who have built multiphoton sources from non-conversion, we know that the generation rates of 3 or 4, well, 3 photons from non-conversion is very low. It's maybe in the order of tens of hertz, no? So this is in contrast with this scheme, we can generate near 100 times those rates. And this was an experiment performed a couple of years ago. Now with the improvements that we have and that we continue having, and that we will soon have anyway, it shows us that these solid state devices are very interesting platforms for allowing experiments in quantum photonics with a larger number of photons. In fact, proof of this is just the experiments that you can see coming out every now and then from the groups of Chai-Yen Liu and Yang-Wei Pan, where they are already performing boson sampling experiments with more than a dozen of detected photons. Okay, So these are just some experimental results of our protocol. If you would like to know more about this, please see the reference, this paper in Optical. I'm going to put it here. Okay, another application, another experiment where we utilize our sources is in this entangling, this loop entangling operation. Basically, the idea is very, very simple. You're using only a single photon source and one single entangling gate used in a loop configuration. You can keep entangling every subsequent photon to the next and so on. And by doing so and controlling maybe the properties of the photon, in this case, the polarization inside the loop, you can create linear class states. There are some proposals to extend this to also 2D cluster states, but of course they are more complicated and we have not yet performed those experiments. Here are some experimental results showing that we indeed created cluster states of 2, 3, and 4 photons. If you'd like to see more details on this, please do see this reference in archive. And let's see for a second. Okay, and maybe some future application that I would like to mention here is this very nice protocol proposed by some people at the University of Queensland, Tim Ralph and Jeremy Milman, this so-called coherent state quantum computation scheme. And this scheme, what it does is uses at the input not single photons like in the standard KLM proposal, but instead cat state, superposition for coherent states. And what is interesting also of this scheme is that the scheme can work with states of a small amplitude with values near actually the values that we already have from our sources. And what is also very interesting from this scheme is that in fact you can perform deterministic photonic gates without the need for nonlinearities. And that's big because that's a huge problem in at least discrete variable quantum photonics to perform entangling gates. So that will be a potential protocol to follow and to try to demonstrate with our sources. One could envision first, one of the first protocols to be implemented would be simply the amplification of the states that we have. We can amplify the cat state that we generate via interference and some ancillary states there and some heralded detection. We could imagine that one of our first protocol could be some experiments of that kind. And well, now I just want to say very few words on maybe some recent improvements that we have had. And as I was describing so far, all these experiments are done under resonance fluorescence excitation, right? So this means that we are exciting our quantum dot with the same color as the emitted signal. But it turns out that it's also possible to excite the system with a very small color detuned source. So now the physics in play is different. It's not the same as in resonance fluorescence. But what is important for us to now know is that you can also get the same quality of the single photon source as in resonance fluorescence in terms of single photon purity and indistinguishability. But what is important in this scheme is that you can sometimes double the efficiency. So I did not discuss too much efficiency values because that was already covered in Nico's talk, but at least we expect that, and in fact we already measure this, and soon we will have our manuscripts available for everybody on this project, where we have seen improvements of our sources by a factor of 2 or even going beyond 50% in some cases. Well, with this, we expect to just get, of course, more interesting results in the near term. And with that, I only want to thank you for your attention, and I should not forget to mention the support of the Marie Curie scheme for funding my research. And with that, thank you, Rowan.
Thank you. So, colleagues, please, questions using hand. Yeah.
Hello.
Paula, you had a question? Okay, Xason, please.
Hi, Juan. Thank you for bringing us this very nice talk. And I have some questions regarding the second part of your talk. When you talk about photon number superposition states, it's kind of it's kind of a miracle for me, at least from what I get from your talk, that you can measure the phase between a vacuum state and a single photon state by just photon counting. Normally, as far as I understood, you need to do some homodyne type of measurements, right?
Yes. Yeah.
And perhaps I missed the point. Can you explain how did you measure how did you manage to measure that phase sensitivity?
Certainly, I can mention that. Okay, maybe I wasn't clear enough in describing what phase I was talking about. So the phase I'm describing here, it is not the phase of the photonic state. Here, the phase that I write here is the phase difference between the inputs of the two inputs of this beam splitter. And it is true what you said, that in order to measure the phase of a photonic state, you would need to perform, for example, homodyne detection. In fact, then I should stress that we are not able to measure that phase, the phase of our photonic state. That is not the phase we're measuring. But instead, what we are measuring is, like, if we just imagine here in the, I actually made a mistake because I used the same letter here, phi, between the, and this is the phase for the state, and that phi here is not the phase for the state. So that is a mistake of mine. I'm sorry. What I want to say now is that we are not able to measure the phase of the photonic state, but instead we're able to measure the amplitude of the coherence. So that's the difference there. We do not know what is the phase of the state, but we know it's fixed, although we haven't constructed the full state, but we know at least if the state is pure or mixed, because if it was mixed, then we wouldn't observe oscillations. And now the oscillations are with respect to a different phase, the phase of the laboratory, the phase of the path length difference between the fibers, if you will. So yes, it is true. We have no information about the phase of the state. We only know the amplitude of that coherence term.
Okay. Yeah. Then I think it makes sense. Yeah.
Yes.
Okay. And for the and also about this photon number coherent states, you said that the G2 of 0 at 2 pi, it's equals to 2.98. This is because the two photon contribution. But as far as I remember, if for a perfect two photon state, the G2 should be 0.5, right?
Yes, you're absolutely right again. And the reason why the G2 is more than 1 here is because really, in order to calculate this G2, it's not only the single photon whose G2 is 0 and the two photon term whose G2 is 0.5 that plays a role. Vacuum also plays a role because the definition of G2 there is normalized, is divided by the mean photon number. And if you have a lot of vacuum, the mean photon number is very small. And therefore, the measured G2 can be larger than 1.
Okay, yeah. Okay, that's all my questions. Thank you.
No problem. Thank you for your questions.
Okay, Paulo Ribeiro, please.
Thank you. So Juan, talk. So is it correct to say that by managing the energy of the excitation pulse, you can control the coefficient of the photon number states in the number state base? Is that correct?
It is absolutely correct. By tuning the intensity of the laser you're driving, you tune the coefficients of the superposition indeed.
Yeah. So, but then, are you able to generate arbitrary to engineer arbitrary efficient distribution, or are you restricted to some classes of states, for instance, coherent states like or thermostates like you just displace the distribution, or you can engineer more complicated stuff?
That's indeed a great question, and we have more research on that line that I didn't have time to explain here. So to answer your question, if you're constraining yourself to the simpler case of only vacuum and a single photon, there you can mostly tune the coefficients because you can go to pi poles, and at that point vacuum is minimized. No, how much you can minimize it? Maybe you can never make it, strictly speaking, zero, but you can mostly tune those coefficients in all the values from 0 to 1, pretty much. But if you are now referring to the state that you generate on 2 pi, including the 2 photon emission, there is some degree of tunability, but basically you have also constraints there. Basically, you can increase a little bit more the 2 photon component, for example, and by doing that, you are also increasing the size of the small cat state, let's call it, that you're generating. And how do you do that? Is you can use longer pulses. So there are other parameters that you can exploit here in your laser, not only in intensity, but if you drive the experiment as well, again on 2 pi pulse excitation, but now your pulse is longer, your laser pulse is longer in time, you will have a longer 2 photon component. But now at some point, all this is very interesting to find out what kind of liberty do you have, because at some point you start generating 3 photons as well. So all that theory is described in this Nature Physics paper of the group of Yelena Vukovic of a few years ago, where they do plot their photon number distribution, the P0, P1, P2, P3, and also even higher values, versus the parameters that you can control in the experiment. So yes, there is some degree of tunability, but it's not arbitrary. You cannot choose on hand, you can put whatever value you want. Now there are other protocols that now we have developed recently that allow you to create other types of state, but at the moment I'm not able to disclose yet those protocols, but all I can say now is that also more states of interest can be generated by the quantum dot. Not only single photons, as we can see, we can make superposition of photon numbers, but also not only those states, there are also other kinds of states that are possible to be created with the quantum dot. And soon, I'm hoping in maybe a month or so, we will have also those results available for everybody. Yeah.
Just only one more question. It's just I've seen a lot about this single photon sources with quantum dots, always in single mode operations. I mean, single mode, spatial mode. Possible to engineer something spatially multi-mode?
Yes, definitely. So the reason why this is a single mode in the spatial degree of freedom is because we are placing the quantum dot in the ground state of the cavity, in the lower energy state of the cavity, which is a Gaussian mode, right? But the cavity itself has higher order modes. They have different frequencies, slightly different. Maybe they are far apart by a few nanometers. And those other higher order modes in frequency also have higher order modes in the spatial degree of freedom. So we could also envision then coupling the quantum dot to those modes instead. And by doing that and forcing that now the light is emitted no longer in the single mode Gaussian distribution, but in that other higher spatial mode. So it is definitely possible. Yeah.
So very much.
Thank you for asking.
So any more questions? Okay, Ranjit, please.
Yeah. Thank you for your talk. I have two questions. First one is, what about level of quantum noise as compared to non-classical states generated by using nonlinear crystals?
Okay. Oof. Let's see. I would like to understand very well the question. You are referring to the noise, for example, in the intensity degree of freedom as
Yes,
compared to
intensity.
Okay. What can I say about that? So let's see. The noise. I'm not sure what can I tell you about that, because what I'm trying to imagine now is the state that is generated by the quantum dot, and this is a very efficient single photon source. So the question will be, what is the noise of a single photon source, right? Like if you draw, or the superposition of a vacuum and a single photon, if you draw this state in the phase space, right? What noise do you measure? So it is. I wouldn't really be able to tell you what do I expect, because these sort of measurements have not been done by us. However, kind of those measurements actually have been done by other groups where they have run their experiment not in the regimes where we run it, like in pi or 2pi, but when they weakly drive coherently their states and they measure this coherence with a laser and coherence with vacuum, they have measured the state in the phase state representation. And if I recall correctly, the noise that they find is the one that you expect of a state of that kind, of a superposition of vacuum and a single photon with those components. So I don't think it's too noisy in that sense, but apart from that, I'm not very sure how to answer the question, or what kind of noise are you maybe thinking of when you say the noise that parametric down conversion generates. Maybe you can instead explain to me what sort of noise do you have in mind from the other sources, and I can try to compare that way.
Yes, the first one is usually you have either it is sub-Poissonian like light,
Yes.
or it is super Poissonian. So this is the first example. And also the second one is, if you're talking about the polarization, then it also has dispersion or the noise polarization. So this is the second.
Okay. No, thank you very much for asking the question. I didn't understand. You wanted basically a comment on, and certainly the noise will be sub-Poissonian. Of this, I'm certain. Now, regarding the polarization, for example, there are some schemes that we are testing now where we can directly measure the polarization purity, right, related to the noise that is emitted by these devices. And we have found, I have not shown any data of that in my talk, but we have found by measurements that the purity in the polarization degree of freedom, it is also very high. I mean, it is nearly, to put a number here, is it can be beyond 99% of purity when you refer to purity here, like the trace of the density matrix of that degree of freedom. So it is highly pure, and sometimes you start wondering, well, okay, what I measure, it is pure because that's the limit, the physical limit of the purity, and therefore the noise in the degree of freedom of our device, or it's also limited by our measurement apparatus, no? So this is something that we will continue exploring, but at least regarding the noise in the polarization degree of freedom that you're mentioning, it is very small. The light can be emitted with very high degrees of polarization. Also, regarding the polarization anyway, there is a complicated game of time-dependent polarization, precession, and evolution, depending on the nature of the device that we have into play. I didn't discuss any of this. It's not very important, but at least to your question, whether there is a lot of noise that we expect in the polarization degree of freedom, this I can answer with measurements that no, the noise is very reduced, and it allows you to have purities in this degree of freedom above 99%. Yes.
Thank you. Second quick question. Is there any dependency on diffraction parameters in your G2 formula? So I see no diffraction parameters. So maybe there are some dependencies on diffraction parameters.
And can you specify to me, please, when you say diffraction, you mean diffraction where exactly?
So when you have generated the photons, so they have like vector k. So vector k, it is sometimes is parallel to your axis z, and sometimes it has some angle.
Okay.
So if you have some angle with axis z, then you have some diffraction. So your beam is just spreading.
Okay.
So in your case, I see you are using pulse. So
yes.
It means that you should have some diffraction.
Yes. Yes. Okay. Okay.
Okay.
Right. If let me try to answer this question the best I can, and if I understood the question correctly. First, on the related to the first comment that you made regarding the angle of emission of the single photon, with respect to this, there is in principle at least no difference that we can observe. Like if we collect light with a slightly different angle or collect a different region with a wider angle in the emission, we do not observe any difference in the G2. Now, what you have mentioned, diffraction and short pulses, and this can have an impact in the G2 indeed, because maybe more than diffraction is really about the pulse length. So the value of the G2 does depend on the pulse length. And of course, if you choose spectrally broader, for example, laser pulses, it will give you a different G2. But the reason behind this is basically every time re-excitation. Usually when you are working in the short pulse regime and below pi pulse or so, you want to minimize this effect, this re-excitation. This is what gives you a second photon, right? Maybe in other scenarios, like when you're driving your quantum dot on 2pi, you conversely want to maximize that effect instead. But normally, well, under normal conditions, when you want the single photon, you want to drive it on pi pulse excitation. You want to do it with a pulse that is as short as possible in order to minimize this re-excitation and therefore minimize the value of the G2. So yes, there is a dependence of the G2 on the pulse duration, and in that sense on the refraction that is possible in your experiment. But it comes from this physical mechanism of re-excitation.
Thank you.
Thank you for your questions.
Thank you. Any more questions? Okay, I have a question. So you said that these quantum dots can be used as a sources of superposition states in photon number space. But is it possible to use this device as some kind of quantum process in this state in order to change this superposition coefficients if you have this state as a pump, for example?
Yeah. Brilliant question. The short answer is I don't know, but I hope so. So indeed, yeah. So you can imagine, right? Like maybe a projector, even like you can think of, okay, any projector is just like the process that generated the state in the first place, but looked in reverse or something like that. So really, we are not sure how it can be exploited, but indeed, we are interested in exploring at least something in this direction, because we want to also excite the quantum dot, not with a laser pulse anymore, for example, but also with a single photon, right? So this goes in the direction of what you're asking. And then we want to see, okay, what happens in the first place if we excite a quantum dot with a single photon? And then what happens if this is a superposition? What do we get at the output? We can try to do some calculations. Do we get entangled states? We don't really know. And also this will be very challenging anyway, because of course we take a hit in the efficiencies already, even in just getting the single photon in the first place. Now imagine trying to feed that single photon with a reduced efficiency onto a device. So it will be complicated from an experimental point of view, but indeed, I don't know. I'm looking forward to find out either ourselves or anybody in the world that is interested in looking into that. But thank you for the question.
Okay. Okay, great. So are there any more questions? Ivan, please.
Yeah, Juan, thank you for the nice talk. I have a question for the application part regarding these amplification schemes. Do they introduce any success probability of the amplification, or it is the deterministic process?
Yeah, no, it is not. The specific scheme I was displaying, let's go there. And yeah, no, it has, of course, some probability of success as most protocols. It is not deterministic, at least this specific protocol that I'm displaying here. What is interesting of this scheme is that there are other protocols that you can perform in order to achieve deterministic photon-photon gate, well, photonic entangling gates, but it's not the one I'm displaying over here. This particular one will succeed once every, I don't remember the number, probably every 10 or in that order of times.
Yeah, okay, thank you.
Thank you for your question.
Okay, any more questions? Okay, it looks like that there are no more questions. So let's thank the speaker. It was very interesting talk. So thank you, and see all of you next week at the next seminar.
Thank you, everybody.
Thank you. Yeah,
see you
thank
soon.
you.
Thank you all. Good to see you. See you next time.
See you.
See you very soon. Ciao, ciao.